And tonight we're going to hear from Nikolay. Nikolay he was a Knowles employee. He started 10 years ago, right? And then about this time last year, our consumer microphone division was spun out. And Nikolay now works for Syntiant. Syntiant is a provider of edge-based sensor solutions, including audio. And Nikolay is going to talk about how vibration sensors work, how they play in that environment, and the kind of things you can do with high bandwidth accelerometers. So I give you Nikolay.
Thank you very much. So first of all, really appreciate the opportunity to be here. Chicago is very dear to my heart. I used to live here several years and started my first professional steps. And actually, Charles was the one who hired me and brought me to Chicago to work for him. Unfortunately, back in the day, for many reasons, it didn't work out on his team, and I got a different team for myself. And the rest is history, but certainly snake is biting its tail, circle is closing, and it's an opportunity for me to reflect on the last 10 years. So really grateful for the opportunity, and I see some known faces here. Great honor, and I expect some challenging questions. So please, even though we're all relaxed and post pizza, please interrupt me, point at the slide, say this is false. I would love that. So yes, I am responsible for applications engineering of consumer MEMS microphones and all the sensor business. Knowles, now Syntiant. Charles did a great job introducing. You left out the most important two letters on the keyword, which is, of course, AI. So it has to be AI. But jokes aside, the value proposition of Syntiant is edge AI solutions. What does it mean? It means no internet, low power. So if something is not connected to the server, it has limited computation power, limited battery life, you want to use your sensors to experience the world, frankly, listen for us today. And then there are, low power, efficient, small processors that run relatively small neural network models that make decisions, detect keywords, detect events. They can convert your speech to text. They can denoise your signal. You name it. And so inside Syntiant, now there's this full stack from sensors to outcomes that is useful for the final user. And so today I will be talking about V2S voice vibration sensor. You might have heard of it before. We've been working on it and selling it for a few years now. And it's a new sensor. It's sort of like a microphone, but actually not a microphone. It is an accelerometer built specifically for voice applications. Today, I will spend the next hour talking about what we've learned. I think it's very interesting of how you can use an alternative sensor for audio applications, and whenever maybe microphones are struggling, and you can supplement it, make it better with these additional sensors. So this is my most technical slide for the day. It's a fun talk, by the way. Yes, this is the most technical slide. So this is the thing. It looks like a MEMS microphone. It's an little PCB board, metal can on top. Looks like a MEMS mic. But I want to bring your attention to a couple of characters here. So what's important is even the most basic sensitivity of the sensor specified, not against pascals, but against G. So it is truly an accelerometer. It's sensitive to motion. And the second most important parameter on this table is the number 10,000 here. So it is built from ground up to have flat response, majority of the audible range for human ear. And so we have to get the vibration somewhere, but if we have it, we can listen to that signal and the sensor will pick it up, and it will carry information that we need to understand the sound, to communicate using that signal. So other than that, it looks like a MEMS mic. Sometimes people get confused about the port. Well, why do you need a hole if it's not listening, if it's just sensing the vibration? The hole is needed for reflow purposes, so it doesn't pop like a popcorn when you heat it up to 250 degrees Celsius, because there's air inside. You need to ventilate it, but for real applications, it's all closed and sealed. So I'm going to keep going, but please, if there's questions, just interrupt me as I go. There are multiple categories of applications where such sensors are useful. There's kind of these three buckets. And sensors of this kind, this is not a unique sensor. There are others trying to do similar things and choosing different design trade-offs for them. But sometimes they're referred to as bone mic or bone conduction microphone or bone conduction listening. So this will be the category on the left. If a device is touching human body, when we talk, we vibrate. Anatomically, the tissue experiences vibration. If the sensor is in contact with that, you can pick up that signal and take advantage of that. Alternatively, I'll be talking about second category, which is, I call it sound-induced vibration. When sound waves propagate through the air, hit the objects around us, they all experience micro vibrations. And if you put a little sensor even on the surface of the desk, you can use the entire desk as a diaphragm and pick up its motion and try to learn and acquire signal that way. And of course, there's always others. Where are some fun things over here at the end of the talk? I'll mention that as well. So let's get started. And my first category is human body contact. So what is the problem? The problem is we've all been in this situation. You're trying to have a phone call with somebody, and the person on the other side of the phone call is in a loud environment, busy street, traffic, office, loud bar, and you're just like, I cannot hear you. Go outside, find a quiet spot, call me back. It's frustrating. It's annoying. Nobody likes it. Everybody uses, earbuds, but they are limited in this category. So what can we do? Well, the premise is that around the throat area, in the mouth, in the throat, vibrations originate, they propagate through the head. And if we put such vibration sensor inside the bud, which goes in the ear, we can pick up very strong vibrational signal that is carrying information about the user speech, and it will not pick up the environment around us. This is the main idea, the value proposition for such application. Well, that's great. So let's talk a little bit about the signals. So I'm very proud of my drawing skills. So of course, vibration, like I said, propagates to the bud and starts shaking it. So can I use my mouse? So yes, typical example of a human speech spectrum looks something like this, sort of a little bit diagonal, like blue on the top chart. Truth is, as the vibration propagates to the ear and makes its way into the earbud, it's not a perfectly mechanically propagating system, and you start losing high frequencies quite a lot. So actually, the coupling into the TWS earbud, true wireless earbud, has this kind of low pass shape to it, and then it all gets multiplied by frequency response of the sensor itself. And so in the end of the day, you get a signal that is different from the microphone signal. So this is an example, a little bit deeper into anatomy of the human. Actually, what we found out, all the information about what you're saying, all the speech content, all the frequencies are present in the bone. So the fun test, most painful of my career, is taking a motorcycle earplug, putting a sensor on it and shoving it into my ear. And so if you press it nicely against the bone, avoiding impedance boundary for mechanical, properties, so from the bones continuing in a firm kind of propagation in the medium, you basically get earplug almost the same as what microphone will give you. Of course, there are some differences here and there, but the big picture, if you normalize just for gain, constant gain across frequencies, you get comparable data. So the information is there. But then you can trade off comfort with signal quality, because you want to have a always on, always wearable earbud, which can be sitting in the ear for several hours and doesn't not, make you bleed. Then high frequencies go away. It has to do with just the softness of the silicon, and they just don't propagate over there. So as a result, the typical pickup of the earbud, which I call here V2S demo, is our demo kit. It's very nice and strong in low frequencies, and then not much left in high frequencies. And so this is the main problem that we're trying to tackle. So first is how to go around it. Maybe we can optimize mechanical design and make an earbud that's magically going to be able to capture that content. Well, the goal is shown on the top in kind of a white dashed line. This is what we're trying to recover over there. We really tried, experimented a lot with various ear tips, materials, orientation of the sensor inside the bud, different brands, different types. It's impossible, basically. Long story short, the only valuable thing that we really found out is that when we talk, vibration of the skull tends to be oriented this way. And so if the sensor with its sensitive axis, because this is a single axis sensor, has to be placed kind of orthogonally to it to maximize the coupling. Other than that, you cannot do much more with mechanical integration unless you go to something that is truly uncomfortable. Okay, it's an evening talk. I need to make some fun puns. George Clooney movie Catch-22 about World War II bombers in Italy. Does anybody know what movie I'm talking about? Maybe?
The older one.
Well, maybe. So what I'm trying to say, they used to have communication systems in the military jet cockpit. I think a version of that is still used today, when there's a special color that pilots wear on the neck, where it's also vibration-based, exactly solving the same problem in a loud environment to communicate over radio, and they wear it directly on the throat to really capture all that signal. Of course, for consumer applications, it's not necessarily viable, and you only get low end. But it's a similar idea.
Who made that throat mic back in the 1940s?
Someone at Sure.
Was it really? Yeah.
So, so I think before I talk about details of signal processing, let's just do a demo. Demo is always fun. So what does it sound like? What can you get out of it? So I have a couple of examples of real world scenarios. This is my favorite. This is a subway station. This is underground. Electric trains come and go, and it's very loud. So this is first is just reference conventional air microphone listening to the environment. Sitting on a platform. That's way too long. This is the harmonics of the train applying brakes and slowing down, and stays on the platform and then accelerates again away. There's actually speech behind it. It's hard to notice it, but I'm talking in parallel. So this is an example of modern headphones set that can do what does it do in the same environment.
Okay, this is a sound test. I have AirPods and vibration sensor.
So they do okay, but there's a lot of adoption of the algorithm. It jumps left and right, trying to optimize the best results. And this is what you get with V2S. I'm actually gonna jump straight to this one, where I played around with filtering and equalization to make it as flat as I could.
Okay, this is a sound test. I have AirPods and noise vibration sensor at the same time. Quiet subway station train is coming. Hello. 1, 2, 3, 4, 5, 6.
So, it gets intelligible speech. You can understand what I'm saying. Is this recording sound quality? Sure, no. But for communication purposes, just a single sensor, this is what it gives you in a very challenging environment. And on the first recording, you couldn't even hear me doing the counting 1, 2, 3, 4, 5, but it does come through. Of course, it sounds like you have a pillow in front of your face, because there are no high frequencies left. It's because it's low pass like that. But when we pitch it to actual customers who design these buds, they tend to say that this is not at the point that they accept as a communication grade quality, but as a extra useful data channels that they can mix in to the final algo that they do on their device, where power and cost and other parameters are taken into account. They find it useful, and we had quite a bit of success with such application. Real quick, maybe another demo. I have airplane. Just maybe there's something, but it's really very loud on the airplane. AirPods.
This is a test. AirPods at the same time.
It's still quite noisy. And again, if I just do EQ on the vibration sensor.
All right, this is a test. AirPods at the same time, microphone as well as BTS vibration sensor.
So yeah, it does the job done to this extent. So I want to maybe go a little bit more details and into a little bit more details and a little bit more technical here. So actually, there's extra problem. So we pick up good signal, what we just discussed, this kind of rich and low frequencies, but also we're assuming you don't pick up any environment because it's vibration sensor, it's not a microphone, so it's ignoring all the environment around you. Well, it's true, but to extent. The sensor by itself, the upper diagram shows it is truly no acoustic sensitivity. It's truly deaf. It was a fun measurement challenge, how to specify that there's no sensitivity. It's actually very fun. You have to build a fixture that shakes but that makes a bunch of sound, very loud, but no vibration at all. We had to bring some bricks into an anechoic chamber and a bunch of metal heavy things to avoid vibration. But anyway, in a real scenario, sound wave will hit the body of TWS and introduce some vibrations just because it knocks it with the sound waves. And that is enough to introduce some crosstalk of unwanted environmental signals that corrupts the vibration channel. And how do you kind of separate those one against the other is a very interesting problem. Kind of this diagram is supposed to capture it. You have the good vibrations coming from here, and then the environment introduces an unwanted signal in the vibration domain. And to get a little bit more technical, microphone on the left picks up picks up sound from the user, which is this good signal, and environment, this bad signal, more or less the same way. It's a microphone, doesn't care. But vibration sensor is very different, and there is a frequency dependency, and the good signal gets coupled this way, and the bad signal tends to get coupled more in high frequencies and a little bit also in low frequencies. And so it opens up a lot of creativity for signal processing. How can you take advantage of these spectral features to get the cleanest output possible? Very fun. The most basic idea is just, okay, let's only take this strong signal from the user and we will not use vibration sensor in high frequencies at all. We're just going to take the microphone, and it's going to have benefit of low frequency isolation, which is great for wind noise, for example. But high frequency, we're just going to give up. But you can do more complicated things, like you can do a ratio of microphone to vibration. And if it's a true signal of the user, it will have certain ratio. But if it's environment, it will have a different ratio of coupling vibration to sound. And you can like do smart decision on that and do like a complicated noise suppression based on it. So it opens up a lot of room for creativity. We are exploring different directions there. But certainly a very fun problem. I should admit, just last comment on over here, one should say, well, what's up with these boundaries on my reference on the AirPods? Well, truth is they also use a vibration sensor, but they use a different one, which only has maybe 700 hertz of bandwidth. And so you can see that there's a lot less noise over here, and they like actually test and change in the algo how much of that vibration signal they mix in, and they take the highs from the Air mic. So, of course, we're not limited to the little earbuds, and you can say, well, any wearable device can take advantage of it. And this crazy chart, I don't expect you to follow every single curve, but you can see the list on the legend. It picks up vibration on a lot of form factors, and every single one of them has to be studied. There's a huge trend right now for smart glasses. Definitely, vibration sensor brings value over there. You can stick it on, big headphones, glasses. What else did I miss? Different ear wearables. And my personal favorite is, of course, the helmet. So these volunteers on my slide, just kidding, these are from the internet. So if you around the world, very often you see people just sticking their cell phone in between their face and the helmet while going down the street on a moped. Number one is, of course, very dangerous, but it sounds terrible. Obviously exposed to wind noise, obviously exposed to traffic noise, but the helmet is great because it has a tight contact to the bone. And so you actually really couple very well. And it's a great example and great application. So this is the same environment. Microphone.
Microphone on the outer shell. Traffic noise.
So yeah, that's not a good experience for phone call.
V2S, location 2, speech test, 1, 2, 3, 4.
So yeah, it's normalized for this loudness over there. So it's basically on a helmet, it works very well. In the wind, it really shines.
V2S, location 2, speech test, 1.
So yes, this is definitely my favorite application, and yes, this is awesome. Or
is the sensor in that context?
Oh, you just between the cushion and the shell of the helmet.
So it's mounted inside the helmet.
Yeah, it's mounted inside the helmet. And I mean, you can be as creative as you want. We were thinking, okay, maybe if you can have a vibration mode on your cell phone, if you just talk to somebody, like in this is a classical kind of hold, and then just have it against your head and then push the button. If it's too loud, go in vibration mode, hello, and then this way have a conversation. It also works very well and picks up the sound quite well. So I think this is all on my consumer section. In summary, I would say it's great. We're taking advantage of a strong signal coming from the body and fighting the loud environment and trying to avoid the vibrations that are introduced by the environmental sound waves. So now moving forward to the next one. Next one is sound-induced vibrations. So this one is similar mechanisms that I just described. but it was unwanted on the left when it introduces vibration of the fixture of the bud. But now, what if we try to maximize it? So effectively, you get a solution of listening without a port. You can put vibration sensor to any surface, to any device, and try to harvest those vibrations, as much vibrations as you can, and try to listen to that signal. So this is the conceptual diagram. Obviously, MEMS microphone on the left has an open porthole. It's a weak point. It costs a lot. It's a pain to integrate. You have to buy a membrane, and they fail. They limit the IP rating of the final device. It's all around terrible. And so solution is to listen without a porthole, just attaching a vibration sensor to the surface, and you get, by design, ultimate environmental robustness. So you can think about all kinds of applications where it's dirty, it is wet, it is not microphone diaphragm friendly, and vibration sensor can bring a lot of value there. And of course, watch is the first idea. So you see the photo on the upper right. This is my colleague doing a test, and this is actually a very small diaphragm, right? It's not much area to pick up the vibrations from the sound waves, but it is enough. You can even see visually on the spectrograms, because the vibration, because the area of the watch is relatively small. You don't get a lot of the lowest frequencies, or like there's a hole in the spectrum clearly. But again, this is what the raw data sounds like.
V2S on smartwatch demonstration. 1, 2, 3, 4, 5.
Again, we're not trying to do professional recordings here. This is for quick communication or even machine listening for like a voice dial for some quick text message through the watch. Why not? Here is another example. If I apply some EQ to get rid of this resonance peak over here, high frequencies, and some noise suppression.
V2S on smartwatch demonstration. 1, 2, 3, 4, 5.
Yeah. I got a couple of faces in the audience. All right. So awesome. I'm not selling anything today, guys, just a presentation. So, of course, you can also do tricks of adding more sensors to boost signal-to-noise ratio. One can argue that this is noisy as hell. We want to have blue background and red signal, and the dynamic range is not super big, and it's quite noisy again. Clearly noticeable background hum. So, of course, there's always ongoing development. There's next generation sensors that we're going to boost signal-to-noise ratio higher and higher. But even today, this is a nice, neat trick. Signal is correlated as long as you put sensors as close to each other as possible. So signal adds in terms of amplitude, but noise is perfectly uncorrelated. They add in terms of power. And so effectively, every time you double number of sensors, you get 3 dB of SNR boost. This is the extent of algebra this night. But you can see the output of the algo with the yellow line giving us a little bit more signal-to-noise ratio. And we're just proving it with our measurements that it does work. Of course, the other application is automotive. So at this point, I have to say that I moved out from Chicago, but, oh, yes?
In the watch example, can the sensor track motion?
Yeah, great question. The sensor is indeed able to pick up low frequencies, but it's not its primary application. It starts rolling off below 10 hertz. So we've done tests when you can, if you want, you can see spikes of every footstep, for example. Will you be able to reliably capture this? I mean, maybe gyro is better for that, but you can also use that low frequency bandwidth for motion detection also. So for automotive, there's a few types of justification. First of all, cars are very dirty. And actually, not the dirt limits the application of microphones outside the car, but car wash. If you imagine, okay, I need to have a microphone listening for the environment outside the car and be able to survive pointing pressure, jet at it. It's quite a challenge. You can say, okay, but we're gonna protect the microphones with very nice environmental membranes and screens. Sure, but you can block the port completely, and then it will be environmentally robust, but then we won't be able to hear anything. So it's not a great trade-off. And of course, there's a lot of value in having a environmentally robust against contamination solution for listening. Why do you need to listen for the environment around the car? So self-driving cars and self-driving applications. I don't see a lot of them in Chicago. On West Coast, they're everywhere. Fun fact: last week I saw in the news. Party was ending in San Francisco, and 50 people called Waymo at the same time, and they had a gridlock because all the robots just went. It was a dead end street, and they just boom, 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 blocked the entire street. What do you do in that environment? So firefighters and police really hate them. And next year, it's a government mandate to have communication capability to a first responder. You want a police officer to be able to walk up to the car and start yelling at it, and a remote fleet operator will be able to connect and resolve the situation for safety, for traffic navigation, things like that. So you want to be able to give communication to first responders. You want to detect siren and pull over if there's an emergency going on. And of course, if you have hands full with grocery bags, you don't want to put them on the ground. Go for a key, open the door, get your hand. You can have a hands-free solution with just a voice command. So we did a lot of prototyping. Seriously, what a fun job. A bunch of tape on the cars to do sound recordings. A motorcycle is a sound source to simulate traffic conditions, and that would be like spinning on a motorbike around the car, which would be recording the sound at the same time. So this is actually what it sounds like.
1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Very close, very close, very far. 3 meters. 5 meters. 7 meters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2.
So what you just heard is example of speech pickup using vibration sensor, no port. Vibration sensor is attached to the side of the car, and up to 10 meters away, what is it, 30 feet, 32 feet, 33 feet, you can communicate, and you can record speech, you can do voice commands, you can do emergency communication. Of course, there's no isolation from the environment, so you heard like the traffic noise in the background and the engine of the car passing by. It records everything. Another thing to point out here is, of course, life is not that rosy, because the king, like for example, the king in the earbuds is battery. They always get the first priority. Everything else is later. In the cars, the first dibs are for wires. They're most expensive. They're most pain. You really want to optimize the wiring and have as short total distance of wires in the car as possible. So whenever we're trying to add something to it, the ears to the car, they want to put them somewhere where electronics is already present. And it tends to be a place with cameras, frankly. And cameras are integrated to have as little as possible vibrations, obviously, to have a stable picture. And so now you're fighting this fight that, okay, you have a approved location to go into the vehicle, but it is full of bolts and clamps and, screws to really make sure it's a nice and sturdy piece over there. And we're trying to harvest vibrations. So it's a fight, but you just heard examples. It is possible. And okay, of course, the grand reveal of the night is on this photo. Ta-da! This is yours truly. We're doing a siren testing. So for siren application, like how do you even test it? Do you like rent a racetrack? That was also a fun day. So we went in the middle of nowhere where nobody would be bothered by except for some farmers. And so this is a test vehicle zooming up and down the road. And this is a siren, so you can buy them. This is nothing illegal there. You buy them on Amazon for $100. And so we're communicating with the driver inside the car, which is rigged up with a dozen of sensors, and trying to record the effects of the, how you can pick up sirens using a vibration sensor. We ended up with a lot of data. There's a bunch of channels. We have video references in parallel. And what does the siren look like on the spectrogram? It's a sinusoid. It's a sinusoid with some harmonics. It's the main tone is just slides left and right, as expected. And so, you can see this vibration sensor data from different channels on the vehicle, and you can see the resonance of the sensor around here, around 7K. But the siren is there. Signal is right there above the noise floor. So we can really try to take advantage of it and play around with it. Of course, if you're searching for a spike in the spectrum, it really matters how you integrate it and what's your FFT bin size. So it really matters how you trade off precision, spectral precision versus temporal resolution. All of these things are pretty obvious. Of course, there's dependency on the distance to the siren source. The further away you are, it's a spherical wave. It dissipates. So very quickly, that target peak that you're trying to find in the spectrum kind of goes lower and lower. But that's the search. So the final kind of punchline is right here. If you start driving faster and faster, it's harder to detect the siren because the vibration of the road introduces more noise into the channel, and it's hard to detect it. And if it's further away, it's also hard. So red, orange, and blue data and green data points kind of show bad, okay, and really good. So for city applications, it's working quite okay. And one more thing, this is my favorite slide. So I admit it is hard to see, but on each row of these pictures, this is front and back view of the car that is driving, and the support vehicle with the siren is where the orange cone is. So one is right here, one's right here, and right there. So if it's in the front view towards the left, detect it on the front left. If it is in the rear view towards the right, that means it's on the left-ish side of the car. So this algorithm is implemented automatically by just looking at the height of the peak. Very often people tell me, oh, but what about like phase array and the beamforming and angle of arrival estimation based on like a delay between the channels? You cannot do it because these are not mics in empty space and not point sensors. We have entire car panel as a ginormous diaphragm. There's a lot of diffraction going on around the vehicle. So really what you can do is just look at the height of the main peak and try to get angle guesses based on that. So no phase is used for angle calculation. Then you can say, okay, so for designing a microphone, which is a vibration sensor slapped on a square meter size of aluminum, what does it perform like? What are the specs for it? Because vibration sensor specs in G's are not really helpful because we don't have references, all of us microphone people. But if you put vibration sensor on a piece of on a panel, that is a microphone together combined, and they can be described using microphone terminology. So this is a frequency response of a microphone made out of vibration sensor on a car door and the side view mirror. So the prominent peak and high frequencies is coming from the sensor, but everything else is the properties of the surface of the host body. And it looks like a forest of harmonics. Many thanks to Michael Pedersen, who I'm sure a lot of you know, who hooked us up with some wonderful COMSOL simulations. It looks like boiling water. There's plenty of little resonances and troughs that like introduce these waves in the panel. So in the real case, I end up saying that yes, it looks crazy, but overall there's so many little ones that it ends up sounding more or less like a microphone. You cannot hear particular individual frequency kind of issue over there. I know, for example, Tom, you're nodding. On your charts, you like 1/12 octave resolution for kind of a human indication, piano key kind of frequency resolutions. That's a lot more finer than that, so it kind of all gets blended together. But you still need to compensate for the resonance. And of course, yes, SNR is not great. It is noisy. I'll say it verbally. I don't have it on the slide, but you get a microphone with signal-to-noise ratio in 50s on a good day. Maybe high 40s, but it's okay for if you're trying to like speak loudly and communicate with somebody as a trade-off to ultimate environmental robustness. It works. So how are we doing on time? Not great, but okay. I am almost done. We have only fun topics left. Oh yeah, Michael.
For that type of application, do you get a benefit in terms of wind noise, or does the wind also vibrate the panel?
It also vibrates it, but it sounds a lot better than an air mic. I think a lot of the wind gust artifacts and the wind noise is really like turbulent in nature, and it doesn't sound as bad, I would say.
At least some benefit.
Yeah, definitely. But then you start picking up like road vibrations, and it sounds like you can hear that. You can experience it yourself if you're like leaning your face against the window of like inside a bus when it's driving. You kind of get this kind of crosstalk over there. It's that. So fun topics. What else can you do? Some motion sensing. I'm gonna go quicker. Stethoscope. When our body, contracts the heart muscle, there are vibrations, and we can compare classical devices against vibration sensor-based stethoscope. So this is very simple, plastic diaphragm with a single sensor in the center, nothing else. No hoses, no fixture. Inside the stethoscope, there's a cavity with a membrane that creates the sound from the vibration of the membrane. This is just a very, very basic prototype. And this is what we get. Let's go straight to the demo. This is rich in low frequency, maximum 200, 300 hertz. No promises on the sound system here, but let's try. It's there, even on these speakers you can hear it. And it comes through a lot better if you wear headphones. So the claim here is that not only you can do RMS, just measure your heartbeat per minute, not RMS, BPM, not just, how fast your heart is going, but, medical professionals, they look at the delays between the features in the output signal, and there's these kind of the first, second, and third, and what's the relative ratio of the times between them. And I learned that cardiologists during their training, they have these little catchphrases which have certain rhythm to them, and they like memorize that sentence which has like a certain rhythm to the syllables, and they like then try to notice it in the sound of the heart. And basically, you can see them. There are these additional features next to the big peaks, so that the data is right there. So, and of course, if somebody's dissatisfied with signal-to-noise ratio, it is possible to use multiple. And this example is 3 sensors combined, and that's directly expected SNR improvement. From 3 sensors, you get 4.7 dB theoretically. So you can do heart measurement. Next is industrial application. So these are crunchy gears and crunchy bearings. So this is a photo of my favorite demo that my colleague put together. So 3 motors, each of them is fit with a vibration sensor on the housing of the gear of the bearing A, B, and C. And A is nice and fresh, nice and shiny. B spent a few minutes in some nasty solution of like acid and rust producing things, just bad. It's artificially aged. And number 3 is just crumbling in your hands. It's really bad. So good, worse, and really bad. And I didn't bring it with me today, but this type of data you get, there isn't much point listening to them. They sound like just the machine is chugging along. But you definitely see the main peak. And as the system, as it wears off, it actually starts going slower. But then if it gets really loose, it starts going faster again for the same kind of force, for the same torque applied. And then harmonics move around, of course, and overall noise shape goes up from good to medium to really bad. And that makes sense. You start having random vibrations of that shaft as the bearing wears off. And so you can detect the signals of for preventative maintenance and, predict when the machine is about to fail, things like that. So final one is a bonus topic. I was finalizing my slides and I realized that one of them already had a Shure mic on it, so I couldn't help myself but show it today. So you can do music recording. On a guitar, obviously it vibrates, and you can use a vibration sensor attached to it to record the sound off of it. It's very easy. It's a tiny sensor. It's quite a graceful solution, potentially. Sure, you can record, but additionally, the premise is that you will only record yourself and not others, because you are attached directly to the body of the instrument you're playing, and you will be rejecting the sounds around you and other instruments that are playing around you. Similarly to what we discussed earlier, nothing is perfect, and other sounds will also vibrate the body of your instrument, and there's a crosstalk from the environment that way. So let's do a demo and a bit of a discussion. But basically, I attempted some measurements of the sensitivity to actually target signal versus sensitivity to unwanted signal. And so this is, I admit this is a cheeky slide, but I pulled up the polar plot for a Shure mic with the cardioid pattern, of course. With vibration sensor, got 18 dB of cancellation at a 90-degree angle. So I produced this little provocative picture, but this is just a demonstration, guys. And so this is an example. So I got here an acoustical and classical guitar. So I'll just play together. So what's happening here is the instrument is played, but there's also music played in the background in the same room. So imagine you're kind of practicing along a song that is playing from the speaker, and this is what you get. Excuse me? What the hell? Oh, I didn't wait. I just didn't start. Okay. Actually, let me start from the beginning. This is the microphone in the air, what we'll hear. Come on. I'm sorry, guys. I lost my train of thought. One more time. This is music and the instrument playing at the same time. And if you listen to it with the microphone, this is what you will get. So there's a song and the guitar playing on top of it. And now instead of the microphone, if you use vibration sensor on the guitar, she's not petrified anymore. Yeah, quite good isolation. Only the target signal is left. So another example is with the classical guitar here. So this is again a conventional microphone, listening to everything. So violin is coming from the speaker, and the guitarist is practicing along with it live. And this is if you use a vibration sensor. So violin is pretty much gone. It requires careful EQ because there's a resonance at 8K on vibration sensor. You want to get rid of that. And of course, it can be done more carefully with like characterizing of exact placement and matching the response with the reference microphone more precisely. But in general, what I'm trying to say is in such application, one can get quite a well isolated single instrument. If there's a band practice and you want to isolate a single person for for mixing it down the line. So yeah, this is my yes, please.
Comparing to a piezoelectric sensor, is there an advantage or?
I don't have it here, to be honest with you. I would say just open topic. I won't say anything else. This is my talk. We talked today about various applications. I hope it was fun. Not much engineering, more like, applications engineering. But yes, this is our little sensor. Any more questions?
Where are you seeing the biggest uptake right now? What area?
Cars. Cars. I'm betting on cars. Because suddenly everybody has fire under their butts because of the legal requirements. And so they really want it. But others are also kind of coming around. There's also very interesting, if you consider AI noise suppression as a potential alternative way how to clean up the signal and loud environment for TWS, you kind of find yourself in an interesting situation how you cover all the use cases you care about. And AI noise suppression works very well, almost all the time, but not all the time. And it famously fails if you have a human speech, somebody's talking next to your shoulder, also human speech, so the algo cannot separate if it's you or not. And so then there's a lot of innovation going on taking advantage of vibration sensor signal in creative ways. So that's also something that's going on. And of course, glasses are hot in 2025. And definitely vibration sensor brings value there also. Yes?
Sort of a follow-on to the question there, but you've got a lot of possible applications.
Yeah.
What those directions they can go. But how much do you feel you have to develop the applications yourself rather than just hoping someone gets interested and finishes the development on their own? Finish solution.
You just described my job. No, the jokes aside, yes, we have to do a lot of the work, and of course, the customers that we work with, everybody kind of expects a simple solution or something that's baked in and just buy it and you're done. And of course, we try to bring it as far along as we can. And that's, I guess, that's our job. We need to help them. And a lot of it is our own development or proof. But then, of course, it gets all reality check when you say, okay, can I scale it to all kinds of ear shapes? Or reality of integration in the car when it's not just a duct tape on the outside, but it actually goes in the proper module, and it has extra weight and the placement is restricted. So there's a lot of interesting engineering challenges there.
So the main way this is different than like a more traditional accelerometer is mostly the bandwidth.
Yeah, it's a great question. I would say bandwidth, size, and noise floor are main axes for performance space of sensors. And I guess you can throw cost in there as yet another direction. and it's very diverse. It's very diverse, but something that is low power enough for a consumer. It is not bulky, not too bulky. That is also robust enough that it will like pass a drop test. And it's wide bandwidth. We are quite unique.
This is smaller than like analog devices, like typical accelerometer would be.
So typical analog devices, accelerometers will have bandwidths of sub 1K, of like hundreds of hertz. I've been challenged on that before, but this is more or less status quo. You cannot record voice with them, but you can record like motion and events like that. Yes, for sure.
All right, so I'd like to thank Nikolay. I don't know if there's any questions. Is that your wife?
It's my brother.
That's your brother?
My wife didn't take my last name.
So I'd like to thank you very much. The tradition is that we give you a mug and a plaque, but all of those I think are in.
I'm ready.
All right, all of those I think are at the convention in Long Beach. So we're going to have to mail them to you. But I really appreciate you coming out and talking with us.
Thank you, and really thanks for the opportunity. And I've heard, we need to sign up for membership more from us. At least we have some Syntiant people here. So, and I have some ideas maybe for some proposed talks for future. So I'll reach out to you. Okay, thanks everyone.
Thank you very much.